I'm going to give a talk that I've been thinking about for a while. I think the original meetup.com synopsis of this talk was that I was going to talk about sort of writing a programming language from scratch, sort of like a very minimal programming language. But the more I thought about it, a lot of that. So when you write a programming language in Haskell, you do a few things. You have to use things like parsec to do your parsing and lexing into tokens and then parsing. You have to write a type checker. So you want to take you want to parse using parsec, let's say, into some abstract syntax representation. You want to write a type checker that checks that syntax representation to make sure it's sound statically at compile time. You want to do various optimizations. And these are all things that it could be we want to generate code. These are things that could all be talks in their own right? And there's interesting libraries for solving all these problems. So I thought, actually, what I'm going to talk about is I'm going to try and cover two of my favorite techniques for writing embedded DSLs in Haskell. So the title of the talk is How to Not Write a Programming Language, parenthesized, not such that I'm going to tell you how to write a bad programming language, but how to avoid writing a programming language in Haskell. So you might, for one reason or another, decide that you want to write a programming language, or that you need a pretty expressive DSL, so you consider writing a programming language. But then the alternative is to sort of leverage the techniques and the power of Haskell to write the language inside Haskell, and that's the embedded approach. Okay, so we get to cut out a lot of these different steps here. So if we're living inside Haskell, if our language is embedded inside Haskell, we don't have to lex anything, we don't have to parse anything, right? Because our syntax is Haskell syntax. We don't have to choose a sensible type system because we're already embedded in a great type system, the Haskell type system. Okay? Type checking comes for free because we just make GHC to do it for us. Optimization, we may want to still do some optimization, and we still need to do code generation. But we've reduced the problem space significantly, right? We only have to concern ourselves with transformations and functions out of our syntax representation. Oh, so I should say, stop me whenever. Should be hopefully pretty informal. I have some code samples. We'll just walk through them, and if anything's not clear, just let me know. I tried to sort of make it as simple as possible, assuming that you know at least type classes and let's say higher kind of types in Haskell. So things like monad, for example. Okay, so we have some problem domain, and we've decided to write an embedded domain-specific language. We picked some terms, aka the syntax representation, for our language. And what properties do we want those to have? Well, we want to have familiar syntax. Well, that's good because we're embedded in Haskell. So if anyone's familiar with Haskell or ML-looking things, they're going to be able to use this language already. We want it to be composable. We want the terms of our language to be composable. So this is going to actually motivate our various examples, and each jumping off point will be one notion of composability, and then we'll go from there. We want our term representation ideally to be typed. They may or may not be typed, but this may be this may be beneficial, right? So we'll talk about that. And we want terms to support static analysis. So there's a trade-off here, and we'll see the trade-off. Whether or not you get more or less static analysis compared to the expressiveness of the language, depending on the abstraction you pick. Okay, so that's the introduction. And this is kind of exercise one, if you like. So the first type class of composition I'm going to talk about is the monoid type class. So is anybody not familiar with monoid, first of all? I mean, yeah. Okay, right. So, all right. So we'll just go to GHCI and ask GHCI what a monoid is. Is this visible to everyone? Mm-hmm. Yes. Okay, cool. So here's the monoid definition from GHCI. It's defined in the prelude. So a monoid is defined for a type A, and it's a very basic notion of composition. Okay, so you have an empty element that has type A, and given any two elements of type A, you can create a third one. Okay, so ignore mconcat because mconcat can be defined in terms of these two fairly easily, but hopefully it's pretty obvious that this is very generic, right? And lots of things are monoids. So strings, for example, if you want an empty string, well, the empty string is the empty string. And if you want to append two strings, well, you just take the two strings and stick them together. Okay. If you have a list of A for any A, that's also a monoid because an empty list is the empty element. And to append to lists is just to concatenate them endwise, right? So this is generic, but it's given meaning by its type class laws, okay? So you want to sort of study this in generality, and the way you do it is to say, I want my monoid to satisfy two laws. So if I append the empty thing onto something, then it shouldn't change what you started with. And if you take three things, then it doesn't matter what order you append them in, right? So if I take three strings, it doesn't matter if I do the first two and append them and then append the third one, or if I append the second two and then append the third one, append the first one on the front, right? You get the same thing either way. And the empty string, when you append it onto something, doesn't change it. So then we say string is a valid monoid, right? And we can check lots of other things are valid monoids too. So monoid is kind of like one of the simplest Haskell notions of composition, okay? So suppose our exercise is, we want to lay out textual documents on the screen, and we want to define a domain-specific language for laying out those documents on the screen, okay? So we go back to the properties, and we want it to ideally be these things, okay? We want to have familiar syntax, we want to be composable, we want to be able to take two documents and compose them in various ways, in nice ways. We want it to be typed, but in this case, and this really goes with it being a monoid and not something else, there isn't really a good notion of typing. If you think about like what type does this textual document have, it doesn't really have a good answer, so we're going to ignore B types for now. And static analysis, we'll get to that as well. So static analysis in this case might be, here's a document, tell me if it contains any links, or here's a document, tell me if everything fits into this page width, for example. Can I display it on the screen? So those are things that are statically determined. You want to know them at compile time, or rather, you want to know them, let's say, before execution, which in the case of a document means before rendering, right? So those are the properties we want. So going back to that list of desirable characteristics, right? We know we want composition, so we want to compose two documents, and a natural notion of composition of documents is vertical composition, right? So I take text document 1, text document 2, and just stack them on top of each other. And we need an empty document to be a monoid as well. So an empty document is just no text, okay? Empty width, empty height, no text. So we can compose and we have an empty thing, so already we have a monoid, right? So whenever you see monoid in Haskell or other languages, the sort of canonical choice of monoid, like the free monoid technically, is over a type A is a list of A, right? So to explain that, I guess you can say you can always think in terms of lists if you want to have if you want to talk about monoids, you can always think in terms of lists. So that should be our motivating example.
What does free mean?
Free, technically, it's a category theoretical definition, but it means it's intuitively you can think of it as any monoid has an underlying type, right? So there's a mapping from monoids to types. Can I go the other way? Is there a way to take a type and create a monoid in a way such that like I satisfy the laws of the class, but I don't add any extra information, I don't make any assumptions that weren't prescribed by the class? Okay, so if you think about given a type A, how do I construct something that has composition and an empty element? Well, a list is a good candidate, but in general it might be something like a tree, right? Because I can compose this and then like each branch corresponds to composing two things. But the associativity law that I said, the fact that you can compose any three things in any order means that tree structure kind of gets flattened down and you end up with just a list. The only structure that like remains visible is the list. So it's a little technical, but you can think of it as like the minimal monoid for a type that doesn't assume any extra laws, if that makes sense. Yeah. I would just say the kind of go-to example, let's say, for a monoid over a type is a list of elements of that type. So we should always have that in the back of our mind. And we know we want to make a string into a document, okay? We want to be able to take any string of text and just turn it into a document that only consists of that string. So why not try the free monoid, the list of A, where A is this thing we want. We want to lift this type up into a monoid. We know we want string, so why not try free monoid for strings or list of string? Looks like a good candidate. So let's extend the type class that we picked for composition, which was monoid, with a couple of extra characteristics that we want our document to have. Okay, so we want our type class to characterize things that are document-like. Okay, so we've said document-like means we have to compose in this monoidal way, right? So we're gonna assume monoid on A. And Haskell in the Prelude has this this class called isString, which essentially corresponds to the assumption that we want to be able to turn strings into documents. Okay, so isString looks like, I might have to import something. Yep. So it's in data.string, and here's from string. Here's isString. So A is string-like if you have a function called from strings to A. Okay, so in my case, I want my document type A to have a function from strings into the document type. So this is exactly what we want, right? We want to be able to lift strings into our document type. So something document-like is something that is monoidal. It allows you to lift strings, and then I also added these two things. Okay, so I want to be able to indent documents. I want to take a document A and take an indent amount, which is an integer, which is, let's say, the number of character columns, and get a new document. And I already have this vertical notion of composition, but it'd be nice if I could compose things beside each other as well. Right? So I can take two documents and just stick them beside with no overlaps. So I'm going to have to pad the left document sufficiently so that there's no character overlaps. Okay, so here's a class for things that look like documents. Given that class, actually I'll just leave that on the top. Given that class, we can write things which use a document implementation, but they don't care which one, right? So this is polymorphic. This columns value here is a document that's polymorphic in the document interpretation, right? So columns consists of column 1 beside a space beside column 2. And column 1 is Haskell vertically composed with C, vertically composed with Prolog, and the same thing for these three things, right? So let's run that. So that's in monoid.hs. I think I called it render. Okay, so first of all, what's the type of render? So render takes a plain text. So plain text is my implementation of a document, okay? So render columns. Oh, so I want to print it. Okay, so here's that document printed in some standard interpretation of that type class, okay? Hopefully you see how this corresponds to what I wrote. So you have two columns, I place them beside each other, and each one consists of three things vertically composed, and there's a space in the middle. They're both beside a space. Okay? So notice that, well, it's not really important for this, but the vertical composition is non-overlapping. Okay? That's built into the implementation. Okay, so we said our candidate was going to be a list of strings, right? So we can write an instance of document for list of strings. We just do the obvious things, okay? So is string a string? Sure it is. The identity function tells you it's a string, okay? Is string a monoid? Yes. Is list of string a monoid? Yes. We just concatenate the strings one after the other, okay? And if you interpret the list of strings as the lines on your terminal, then that's the vertical composition that we wanted, right? Can we indent a list of strings? Sure, the map function. So if I replicate the number of spaces I want and then map that over my list of strings, just insert a number of characters on the front, space characters, that'll do the job. Can I implement besides? So if I have two lists of strings that represent rows on the terminal and I need to pad them, well, sure. So I can use zip width or a variant of zip width, right? Zip the two implementations of the text, but you run into a problem. How do you get this nice padding behavior here? So how do you know that C has to be indented by what, 6 characters? List of string isn't enough, so we need to actually add more information to our representation. And here's the representation. So we just add on. Here's the list of strings that we wanted, and we just add on the document width as an integer property. Okay. So in this case, the free implementation was not quite enough to do exactly what we wanted. We could have implemented something with the free implementation, but it would have ended up so that you didn't get the nice sort of padding property when you did horizontal composition. So the point is we can, given this document type class, so we pick So this is going to be like the motivation for the rest, right? We start with a class that uses standard notions of composition. So we started with monoid because that's the composition we wanted. We built up a class that determined the sort of operations we wanted on our candidates for our carrier type for our documents. Okay. But we can pick multiple implementations, right? So we could have picked the free implementation, which was list of string, but we picked this one because it allowed us to render slightly nicer documents. Okay. But you can also ignore structure, right? So we added structure here. That was adding an integer width. But we could take structure away, right? Maybe I only care about the width, and I don't even care about the lines. Maybe I just want to sort of simulate rendering something, right? Just to answer the question, does this fit inside a given width? And that answers the static analysis question, right? So we can pick instances for our type class that do more or less than the original task. We're just trying to sort of abstract over the operations that we're interested in, right? And that's what this type class approach does. Okay. Any questions? Because I'm gonna do a few more examples. It's gonna ramp up a bit. Yep.
What's the double caret operator amount?
Oh, right, this one. That is just a synonym for, or I guess it doesn't tell you, but it's a synonym for mappend in the monoid type class. So if that wasn't clear, sorry. So here is where we're doing our sort of standard monoidal concatenation, and we said that that would correspond to vertical composition. Any other questions? Okay, so the gist of the talk is going to be I'm going to set a bunch of DSL related problems and kind of solve them all in this way. And you'll sort of see the trade-offs given the properties that we wanted. You'll have various trade-offs for those properties. Okay, any questions before I carry on?
Actually, I have one question. So we're tracking the width, but it seems like we could calculate the document width from, like, by taking max width of the other ones.
Yeah, I guess you could do that. That's a good point. Yeah, so you should do that, I suppose.
Would that be less efficient?
Yeah, I mean, I guess you can consider it an optimization in that case, right? Atom. Oh, well. So here's my implementation. So it just turns out beside was sufficiently complicated, right? I had to do a variant of zip width and all these kinds of things, and yeah, so you'd have to do a map, right? You have to do a max, and then every time you're interested in finding the width. So I guess you can call it like a small optimization just to save the width. But yeah, I suppose you could just use the free implementation in that case. All right, so the next one is applicative. Okay, so applicative, has anyone? Yep, sure.
Is there slides available?
Yeah, they are. They're on. I guess you can't see it very well, but so it's right here. They're on GitHub. I'll just read it to you. So my username is PAF31, and the repo is Haskell-slides. But I'll put it on the meetup page at the end of this. So.
What was your handle?
PAF31.
Okay, cool.
All right. Okay. Who's familiar with the applicative type class? Oh, I guess who's not? Okay. All right. Well, I'll go through this one. So applicative is, let's see. Well, let's look at the definition first. So we need control applicative. All right. Here's the applicative definition, right here. Does anyone not know what a functor is? I can explain it if necessary. It's okay. Just okay. Good. So applicative is we want some notion of composition, right? So again, it's a notion of composition, but it's typed this time, right? So well, maybe that's not a good way of describing it, but you have an extra type argument. So monoid was you had a monoid for something of type A, right? So A was a base type. So string is a monoid. But string isn't an applicative. You need to have an extra type argument. So something like list is an applicative, right? Because list takes a type argument A. So it's the type constructor itself which is applicative, not the base types, if that makes sense. Okay. So let's say we want to, what's a good example? Well, what's my, okay. So let's say we pick list, okay? f is going to be list. So you need to implement these various functions, but again, these bottom two can be implemented in terms of the second one, so we're just concerned with the top two. Can we implement a function pure that takes any type, a value of any type A and gives back a list of A? Sure, that's, we just give you back the list with one element, okay? And then this operator, can I take a list of functions and a list of values such that the domain type of the function is the same as the value type and give back a list of values of the codomain type? Sure, so I take every pair, so I take for every function and every value, I'm going to pair them up, apply them, and give you a B back, okay? So that's how I can turn a list into an applicative.
Codomain is the European word for range?
Codomain B, yeah, thing on the left of the arrow domain, thing on the right, codomain. Range, yeah, sorry. So what's the intuition for an applicative functor? Well, if you squint a little bit and look at this definition right here, and remove the F's, then it looks like regular, sort of, I guess it'd be the dollar symbol, right? It's just function application. So you can think of applicative as a generalization of, well, let's say it's a model of a language where you can assume function application. But instead of just regular functions, I have them wrapped in this F. Okay, so you can think of F as tracking some notion of side effect. So my example was list. Okay, so how can you think of? Yeah, sure.
Is it okay to use fmap?
So fmap is defined in functor. Okay, so every applicative certainly is a functor. It's a slight sort of like there's a slight difference about how you interpret the application. The function in the functor case has to be kind of a pure function, right? It's just a regular function. In the applicative case, if we think about f tracking effects, both the function and the value can have an effect. Okay. So if we think about list, how is list a model of a language that that has function application, right? So we have to interpret that sort of like taking all the pairs operation as function application in a general sense. Well, the answer is you can think of the list applicative as talking about multiple worlds. Okay, so if you sort of think generally enough, then you can think of working in the list applicative as working in a regular programming language, but where every value could have 0 or more values, right? Real values. So you're modeling so applicative is modeling the side effects of multiple return values, multifunctions. Okay, does that make sense? Some of this is a little bit sort of like hand wavy intuition, I guess. But hopefully, when I give the example, it will be a bit clearer. So, point is anyway, you can think of applicative as modeling a language where you can assume application of functions inside the language. Okay. So here's our exercise. Define a DSL for parsing routes in a web application. Okay. So if you've done route parsing in well, I think this looks exactly like Sinatra, right? I don't really use Sinatra, but I'm pretty sure it looks a bit like this. You type this as a string and then it turns it into a parser for you. So you have something like foo bar baz, where bar is a parameter, right? So I want to match something like /foo/abc/baz, and my parser should say, yes, it's a match, and bar equals abc. Okay. So before, when we did documents, we said we talked about this typing. It's nice to have types, right? But there wasn't a notion of typing for documents. Well, there is a notion of typing for a route. Like if you ask the question, what's the natural way to type a route? Well, you could think of this as having type string, right? Because there's only one thing to match. There's bar, and bar's going to be a string in the middle there. So you might as well think of the route as being sort of like string as its kind of like underlying type, right? But what if I turn baz into an argument as well? Well, I might as well think of that as something with type 2 strings, right? Pair of strings, because I have a string for bar and a string for baz. And the other property is that hopefully we're going to be able to apply static analysis to these routes and answer questions like, given a routing table, does it contain any redundant routes? Are there any routes that I can't possibly hit because it got hit by something earlier in the routing table? Or is a route a sub-route of another? So, for example, foo bar baz is a sub-route of foo bar, right? I want to be able to recognize that. So hopefully whatever we pick should have these properties, right?
The longer one is a sub-route of the shorter one?
Well, yeah, I guess you can pick either way, but it doesn't really, I mean, I'm not going to answer that question. I'm just trying to give an example of, yeah. Okay. So actually I gave a talk like at the Haskell group a while ago and like tried to present this viewpoint that monads and applicative functors are all about modeling languages. And it can be a talk in its own right, I guess, but so the kind of the jump that I want to make is we have this notion of typing, and we want to be able to apply functions, right? So if I'm passing this one, for example, and I want to turn that into something which isn't necessarily 2 strings, but it contains 2 strings, I can build it up by function application. And I can kind of think of that as effectful function composition. And if applicative functors are models of languages with function application, then you know an applicative is probably the notion of composition that I want. Okay, so I said that applicative was typed, and the notion of typing that I sort of like hand waved over up here, and I said this is 2 strings and this was a string, that's going to be my type argument. Okay, so I'm going to try and find some applicative functor such that the type, if I instantiate the type argument to, let's say, 2 strings, that type would instantiate to a parser that would be able to parse routes of that type. Okay, so all right, we'll get to the meat of it anyway. So here's the here's the main point. We're going to do what we did before and create a type class for describing applicative functors that look like route parsers. Okay. So I tried to motivate why applicative was the right concepts for composition. And just like before when we wanted to take a string and embed it inside a document, now I want to be able to take a string like foo up here and turn that into a parser that just matches foo. And doesn't sort of match any content, just looks to make sure that foo is at the front of the current route. Okay, so again we have this isString constraint, and we have applicative for our composition. And my additional thing that I want to add to this is match. So match says I want to be able to parse something that's a string. So whatever interpretation you pick, whatever f you pick, you better be able to read a string. And reading a string should mean, let's say parsing has gotten up to bar, then it should be able to make sure there's something next in the route and assign it to bar. Okay. So if I do match followed by, if I use the applicative composition operators to do match twice, then it should be able to match things like 2 strings, bar and baz here, right? And then I should be able to apply a function like the tupling operation and get something out of type 2 strings, for example. So here's how I would parse things that look like foo, bar, baz that I had before. Okay, so again, just like before, like we were polymorphic in the document type, now I want to be polymorphic in the route parser implementation, right? So given any route parser implementation f, I can give you back 2 strings, a pair of strings wrapped with whatever effects f had to choose to be to do its work. Okay, and the implementation just uses the applicative combinators. So oh, there's an equals sign here missing. I'm sorry. So I should say route equals the rest. But route equals. This is how you use. This is typically how you use applicative in practice. So you have multiple arguments. So here's argument 1, here's argument 2, and you separate them by these 2 operators here. So you can think of this as applying the tupling operator here to the 2 arguments, foo followed by match, and then match. Right. So foo doesn't return anything, so I just ignore whatever it returns. It's just the unit value. Okay. So I do foo and ignore it, and then return whatever match returned. So that's my first argument. And my second argument is just match a string, and then I apply the tupling operator to both of those arguments. So that should hopefully match. Oops. That should hopefully match this, right? Because I'm matching the literal foo followed by a match bar followed by a match baz. So my first string is whatever bar matched, my second string is whatever baz matched, and I apply the tupling operator. And I hopefully get 2 strings. So am I in the right module? Huh. something here. Okay, good. So I said the goal in the document case was that we've picked this type class, right, and we want to separate specification from implementation, so we can have multiple type class implementations for whatever class we pick to abstract over our documents. Same thing with the routes, okay? So we can pick multiple implementations of route, for example. Two implementations are an actual parser, right? So we can do something like parsec and actually parse routes. So I guess I call that match route, okay, and that's here. So match route, we said it had to take a type argument, right? So to match something of type A, my implementation, my choice of representation for my parser in that case is something which takes a list of strings, so that's going to be foo bar bars, or foo abc xyz, let's say, takes that list of strings and returns maybe, because it can fail, an A and another list of strings. So parsing is going to give you a result if it succeeded. It's going to give you nothing if it failed, and if it succeeded, it's also going to give you whatever it didn't match. So that's the remaining strings, okay? Those are the remaining strings. So this is all implementation, but notice then I just start defining instances, right? So I define applicative, which entails functor, so I have to implement functor. Is that a functor? Sure, so I can map over the type A there, right? I just go inside the function and do the mapping. Is it applicative? So applicative said I had a parser of functions and a parser of values, and I have to get a parser of the results. Can I do that? Well, sure. So it's a little tricky, but I can take my initial set of strings, I can run it through the first parser. That parser either succeeds or it fails. If it fails, then the whole parser is going to fail. If it succeeds, then I have a function, because my first parser gave functions, and I have a remaining set of unmatched parts of my route. Okay? Then I have another parser that returns value. So I have a function, an unmatched set of strings and another parser. Then I can pass the unmatched parts of my strings into the second parser and hopefully get a value. Again, it can fail. And at the end of the day, if everything works, I get a function and a value, and I just return them. And whatever the second parser left over, that's what the whole parser returns. Does that make sense? Yeah.
I've got a question about string to the right of the maybe A.
Okay, yeah, sure.
Aren't you really thinking of a pointer to within the string, like where foo is?
So this isn't the same string. Okay, this is maybe I missed the point, but this is a completely separate string, right? So it takes a value which is a list of strings, and it'll try to construct an A and a whole different set of strings that was the unmatched portion. In reality, if you think about like the object graph, yes, it's going to be the same one, but we don't care about that because of like purity, right? There's no way you can run into issues there. But if you want to think of it as like, yeah, it'll be a fragment of the initial string list. So, yeah.
Sorry, the list of strings there is after splitting on slashes.
Mm-hmm.
Yeah.
Yeah, exactly.
Thanks.
So here's how we actually run this thing, right? So somewhere in here there's going to be a split on slash. Oh, here it is. I actually ended up writing it myself to handle some corner cases, I think. So this is doing the splitting on slashes. And I want to filter out the bits that it found that weren't null. So if they accidentally typed in 2 slashes, then ignore that. And then we do our parsing, and then we're going to hopefully get back an A and a string, but I only care about the A, so I'm going to fmap first over the result. Okay, so that's applicative, right? So we have this composition. We can parse to a function, we can parse to a value, we can apply those if they're both successful, and get a parser out as a result. But the class we were interested in implementing was match route, right? So match route said I had to have, I had to be able to give you a, route. Route said I had to be able to give you an f of a string just by matching something like bar and bars, okay? So how do we do that for match route? Well, we get a list of strings as our input, we call it s's, and the only way that it can fail if s's is empty, right? So in that case I return nothing. If it's not empty, I can match out the head, so s is the head, and in that case the result is going to be the string that I matched, so everything type checks, right? I needed an f of a string. This is the type I needed to match, so that's a string, and then the things I didn't match, well, that's just the tail of the non-empty list. Okay. So I had this polymorphic route somewhere in here. I guess I didn't put it in here. That's okay. So let's see. I called it match rate. So match rate takes match rate takes type match rate. But match rate is an instance of route, so I can use route, the type class, to construct my routes. Okay, so let's just do something simple. So I want foo followed by a string. List with no one spot my stupid error. Oh. Actually need an operator here. Getting these operators right can be a little tricky sometimes. Obviously missing something here. Match rate A, string. Oh, yep, okay. So I need to set overloaded strings extension. Okay, so good. The really basic case, right? The foo route matches foo. Does it match bar? I hope not, right? So that returns nothing. What about my other example? Okay, good. So foo with a match matches foo bar. It gives me bar back, right? But applicative is all about applying functions, right? So let's make something more interesting that applies an actual function. So let's apply the tupling function. This was the example I had before. So my first argument to my generalized function is going to be foo with a match. My second one is going to be baz with a match. Okay, that should fail, right? Because there's extra stuff that I expected that isn't there now. But now foo bar baz bam. Okay, that works. Okay, so now I've lifted up this function application of the tuple into this language that has parsers, into my DSL. Okay, so applicative is all about these typed languages where you have this notion of function application for multiple arguments. So if you know a priori that that's the kind of composition that you want, then applicative is a really good thing to base your language around. Okay, so I know this is ramping up pretty quickly, so any questions and go into more detail? Hopefully, once it gets a bit more concrete at the bottom of each one of these, it starts crystallizing, but any questions?
So can you go back to your console for like 2 seconds? Your audio was blocking that.
Sorry, yeah, sure. Oh, there you go.
Cool.
So
does match just take the next word?
Yeah, it just matches any string fragment from the route. So you can make more interesting things. I actually didn't add a bullet point for this, but didn't mention it. So we can add more members to our class if we want to support more operations. So why is that handy? So let's suppose I want to match integers, right, or I want to match booleans. Well, I can do that already because I can match strings and I have a functor instance, right? So I have a function from strings to integers, let's say, just a parse int operation. So why do I want to add something to my class here? And the reason is, if I want to do static analysis on these, if I want to analyze these routes without actually running them, it's useful to be able to differentiate a string match from an integer match, for example, because then I can answer questions that have different answers depending on whether you used a string or an int match. But the point is, you can add more operations to this. So this was really basic, right? Just match the next string. But I can add operations for like match an integer, match a boolean. Maybe I want to match, let's say, query parameters like question mark, ampersand query parameters in the URL. And I can add that functionality here. Actually, at the end, like I've been using some of this for work for actually this application, parsing rates actually on the server side. And I can show that in a little more detail and how you like build this up into something kind of real world, if you like. Okay, So the title here was static languages, applicative, but I didn't really say what static meant. Static in contrast with dynamic languages that you get from the monad abstraction. Okay, so monads, I guess, applicatives, like I guess more straightforward, but more people have heard of monad. Anybody? I'll go over monad anyway, but just out of curiosity, who knows about monads? Okay, okay, good. All right, so why do monads model dynamic languages? So,
What is a dynamic language?
so not dynamic in the typing sense. Sorry, what I'm trying to get at is notion of like data dependency. So, if you think about applicative, all you could do with an applicative was take a function of multiple arguments. Let's say this tupling operation. And arguments with the right types and slot them in and combine the effects, right, and do the function application. But the arguments themselves couldn't influence each other. There are no data dependencies that are expressible between the arguments, right? So I couldn't say something like, look for something that starts with foo bar, starts with foo some string, then look at that string and decide whether I want to use parser A for the tail or parser B for the tail, depending on whether it was capitalized or something, right? So you can't express data dependencies for the second argument on the first, depending on the result of the first argument. They're completely independent. That's good for static analysis, right? Because data dependencies kind of get in the way of static analysis. I can't, if this can match absolutely anything, and this depends on what it matched, then in order to do any sort of static analysis on what this does, then I need to sort of like feed potentially infinitely many simulations into this, okay? So data dependencies are bad for static analysis, but they're great for expressiveness in your DSL. And that's the trade-off between the static side of things, which is applicative, and there's other kind of abstractions in the middle, but and the dynamic side, which is monad. So sometimes you want the expressiveness, right? You want to express data dependencies, and in this case, I want to express data dependencies. In other cases, you might not want to, and you buy yourself more static analysis power by sticking with applicative. All right, so exercise 3, I guess, is define a DSL to give users restricted access to the file system. So I want to define a language. Maybe I want my users to have limited access to the file system for scripting capabilities in my application for whatever reason. But I don't want them to be able to do an RM, RF, whatever, right? So, so I need to cut down the language to a list of pre-approved primitives, right? And give them some means of composing those primitives into like command sets. Okay, so monad is good for that because I said I wanted to be, monad's good at if you have data dependencies. And if you think about a really simple script, I'll skip ahead, but here's a script with a monad, right? So do notation indicates that we're using a monad. I want to do ls, get the files out. And then for every file, I want to call cat and provide cat with the files that I got out of ls, right? So here, what I do with cat depends on what ls gave me back, okay? So there's a data dependency. So you may or may not, depending on your interpretation, be able to do this with an applicative, but you can definitely do it with a monad, right? Because monad is good at expressing data dependencies. Okay, so let's go back. This time we want the user to be able to write sequences of commands where commands depend on previous results. Data dependencies suggest a monad. Okay, so I have like a bunch of these. I guess you just build these intuitions, right? Like applicative is good when you want static analysis and you want to be able to lift function application. Monads are good when you have data dependencies that you want to express in your language. So just like I said, applicative with models of languages with application, you think of monads as models of function composition in other languages. Okay. So think of function composition as expressing a data dependency, right? So the one program feeds its output into the input of another program, and that's function composition in this bigger language. Okay. But with more expressive power, you lose analytical power, right? You can't do as much static analysis, and that's the trade-off you have to decide. And as I say, it's more sort of nuanced than that. Like there's other abstractions in the middle, but these are like the two extremes, I guess. All right, so we'll do the same trick. Define a type class, and we're probably going to have multiple interpretations like we did for parsing. Okay, so here's So I start with, I guess I should show the monad type class, shouldn't I? Info monad. Okay, so if you are a monad, then you are required to be an applicative. And that's good because that, you can think of that as saying, if you can express dynamic dependencies in your language, then you should be able to express everything that was static because that's a special case. Okay. And the two interesting functions are, I guess we can ignore fail and we can ignore this second one. So we're interested in 1 and 3. 1 and 3. So return is the simpler one, right? That takes, you think it's just like pure from applicative, right? I take a value in my base language, which is Haskell, and lift it up into my bigger language that's, that I'm trying to model composition in. And you have this operator called bind. Okay, so I have an M of A. So you can think of this as an effectful A. And I said I had data dependencies in this language, right? And this is where they come in. So I run M of A and I get an A out. Then the second computation, which is M of B, can depend on the A, right? So I pass in a function that takes the A that I got out of my first computation and gives me a new computation that has type B. And I thread those two. I have to be able to combine these two things, right? So an effectful value and a second effectful value that has a data dependency on the result of the first, and combine those into one big computation. Okay, so that's monadic bind. And so like I say, you can think of this as modeling
Does
composition.
MA get run and MB does not get run?
No, MB gets run.
Okay.
So do notation is just desugaring into that bind operator, right? So this is running the first operator, which is ls. I pick out whatever it matched, which was files, right? And then I pass it to, it doesn't depend directly. It depends via this function map first, but I pass some result of that to cat, the second operation. So cat definitely gets run. I'm going to do ls, and then I'm going to do cat with the result. So they both get run, so it's kind of like a sequencing operation, but where one can depend on the other. All right, any other questions before I carry on? All right. So here's my monad type class, and I'm going to extend it, just like we did before with monad and applicative. I'm going to define this monad file system. So what's an M that is a monad file system? Well, I better be able to change directory, right? So I can take a file path and relative to the current directory, have some effects, but I don't return any value. I'm only concerned with the effects here, right? So you can just think of this as an action, just change directory, but you don't have any result. I can do an ls. So ls is list all the files in the current directory. So with effects m, whatever interpretation I pick, return a list of pairs of file paths and file types. So I didn't write it out, but file type here is file or directory. So that you can track, for example, whether you change directory into a directory and not into a file, which would be an error. And concatenate a bunch of files, right? So take a list of file paths and concatenate them effectively into one big string. Take the contents, concatenate them into a string. Okay, so what kind of monads are monad file systems? Well, I/O is like the sort of standard, the big monad in Haskell, right? So I/O you can think of as like the effectful monad that goes out to the world and has effects on the real world. Well, I should definitely be able to interpret this in I/O, right? Because you can think of bash as kind of living in I/O. I didn't actually write it out, but if you look in like system.io or whatever the module is that goes out and actually implements these things in Haskell, their types are going to look a lot like this. So you can give an instance of I/O for monad file system, for I/O, and then I can interpret whatever I write. So I can interpret join files, for example, inside I/O, right? And then here you have this sort of like ambient like state, which is the current directory. In I/O, the current directory is just going to be whatever directory the application is living in. Okay, so just to go through these bullet points, we can interpret in I/O. Users can't do arbitrary things, right? They can't delete root. They can only use these things to write their programs if they stay polymorphic enough. If they write their program in I/O, right? If the type here was I/O of string, then sure you can go and delete root, right? But if your type is sufficiently polymorphic, then the type system will restrict you to only being able to use these things. So the user can't do anything. They can only use the primitive that you provide. And with a bit of work, you can turn this into a DSL that gives you the full power of Haskell to combine the primitives of shell scripting, right? So you can write a shell scripting language as an EDSL inside Haskell. And people have done this, right? So like if you look up, I think it's called Turtle and Shelly are two examples of, I don't know if they use this approach. But the idea that you can build an EDSL for shell access inside Haskell, and you have the whole Haskell standard library with which to build your programs. And just as a note, this approach here where we're extending monad with some set of monadic actions, this is the approach taken by the MTL library. So that's the monad transformer library. So if you ever heard of classes like monad state, monad error, monad writer, those are type classes that model features of various DSLs, and you can piece them together by taking the classes that you want, right? So you can say, I need the ability to write a log. Turns out that corresponds to monad writer. I need the ability to lift up IO actions. That corresponds to monad IO. Okay. I also need the ability to throw exceptions. That's monad error. So I just combine all these, smash all these three type classes together, and that's my model of my DSL. And that's the approach taken by the MTL. So yeah, what I just said, type classes can be composed to combine various features of our languages. Okay. So you don't have to use the full IO monad, right? We can come up with interpretations. We can do static analysis inside a fake file system, like a virtual file system. So here's a fake file system. It takes see this zipper. I implemented this. I'll show you the code. So here's the type class, and here's that file type thing that I left out. Here's that join file script. So instead of using I/O, I'm just going to model my language. The users can just run against this virtual in-memory file system, right? So file system FS consists of a bunch of files. So a file has a file path, and it has some content, which is a string. And it has some directories in it too. So a directory is a file path, and a directory contains a whole virtual file system inside it. Okay. Just to implement things like CD, we need this notion of where I am in the tree. So I use a zipper. If you're familiar with the zipper data structure, it's kind of like a variance on it. But it's not really important. You can think of zipper as being synonymous with the file system. So my fake model of the file system, something in a computation in that fake file system that returns something of type A, takes my model in-memory file system and returns an A and a new file system. So I take the whole file system in memory and just wipe it away and give you a whole new file system back. And that's my fake model. And then I write instances, and then the users can just write scripts, right? They can write their shell scripts in monad file system. And then I can choose to target I/O. You can actually go out to the real world and do I/O, modify files or read files. Or I can give you this fake file system, but you don't know because the type system only told you that you had a monad file system. Didn't tell you that you had an I/O or a fake file system. That make sense? Okay, any questions? The last one's kind of the really fun one, so relative to how fun these ones were. All right. Okay. So, if you're interested in reading about this, the first three were an example of what's called finally tagless style. So there's a paper by Oleg Kiselyov called Finally Tagless something I've forgotten. But if you look up finally tagless style in Haskell, this general style where you pick a class about your abstraction of how you want to build your terms of your language, and then you choose multiple interpretations. The paper's really interesting. I definitely recommend giving it a read. Okay, so the last, how am I doing for time, by the way? Okay? Yeah? Okay, good. Okay, good. So the last example is, the best description I could come up with was models of lambda calculus. So the technique is called higher order abstract syntax. And again, it's well worth looking into. It's really interesting. But it's a really neat technique. It's one of my favorite techniques for building embedded DSLs. So I'm just going to give a really high level overview. And then if we have time, I'm going to actually try and like show you how easy it is to build a language using higher order abstract syntax. Okay. So the really general exercise is define a DSL which embeds the full simply typed lambda calculus. Is everyone familiar with simply typed lambda calculus? Okay. Yeah. Shall I go over it? No? All right.
Yes.
Yeah. All right. Cool. All right. So I'm just going to do it in the text editor, right? So I'll just do it here. So lambda calculus is, you can think of it as a really stripped down version of the functions that we have in Haskell. You only have 3 types of terms. So you have terms like A, B, and C. Okay, those are names for values. Names for values. You have function application. So I can take a function f, which so f is one of these values that I just introduced. A is another value, and I can take f and apply it to A. So I have function application just like I do in Haskell. So a bad example. That's Haskell code, right? But it's also a term in the simply typed lambda calculus. This is a function I can apply it to another name for a value, which is message, which better be a string. And then the third type of term that you have in the simply typed lambda calculus, we have names for values, which are just identifiers. We have applications, which I'll just indicate with stick the names next to each other, like we do in Haskell. And the third one is corresponds to Haskell's lambda abstraction, right? So something like this in Haskell, where you have a function binding a name, and then another term inside, right? So here's a valid term in the simply typed lambda calculus. An abstraction over f, which gives back an abstraction over a, which gives back an application of f to a applied to a, let's say, right? So it parenthesizes like this. So these are the terms of the simply typed lambda calculus, okay? So if you can, like ML and Haskell and various other languages are all built around the simply typed lambda calculus, right, with various extensions. So if you can interpret the whole simply typed lambda calculus inside your program, then you have a pretty expressive, inside your language, sorry, then you have a pretty expressive language. So it'll be a nice model of, if I want to model a full programming language, rather than just a DSL, let's say, rather than like a toy language, let's say, like we did with the parser and documents and things, then it's a nice abstraction to use. So higher order.
Can you have a lambda calculus without having the concept of number or string or any of your data?
Yeah, sure.
Really?
So
interpretation.
So well, you can choose to interpret it in different ways, right? So I mean, in practice, are you going to do that? Probably not. You can get a long way with just functions, right? So you can model things like integers and natural numbers and integers and rationals and addition, multiplication, etc. with just functions, but it's not code you'd write in the real world, right? But so this is an abstraction that, like, just like I said, we can extend the monad file system with other operations. In practice, we're going to extend this with other operations, right? Like maybe I extend this with like true and false and if then else for booleans, and I extend it with like integer literals and addition and all these. So I just build up my theory with these different type class extensions. Okay, sorry. So that's simply typed lambda calculus. We want to model it. Okay. So yeah, I just said we can craft a functional programming language using. So I mean, a functional programming language is essentially defined by, is based on lambda calculus, right? So this will be a functional programming language. And I'll provide a core set of functions, so just like we were just saying, right? In practice, we want more than this, but it better have this at the core to be a functional language. So I might extend it with booleans, I might extend it with integers, I might extend it with just other interesting functions that apply to the domain that I'm working in. But the user gets all the abstraction afforded by the simply typed lambda calculus because this is at the core, okay? So just like we defined a class before, now we define a class for our higher order abstract syntax. So variables are actually going to be baked in, right? I'm going to use the variables, I'm going to use the names for variables from Haskell. But I'm going to use my type class to define the other two primitives of lambda calculus, which were application and lambda abstraction, okay? So just like in the applicative case, f is going to have a type argument, right? So I have f applied to something. So if I have, let's pronounce f a as a model of a, let's say a model of a function of type, a model of a value of type a, right? So if I have a model of a value of type a to b, and a model of a value of type a, then I can give you a model of a value of type b. And if you remember the applicative type class, that looks a lot like the applicative operator, right? That did the sequencing in an applicative. So if you parenthesize this on the right, okay, fa to fb is parenthesized here implicitly. Can I give you an inverse to that? Can I switch those around? Right. Well, if I did, that would look a lot like lambda abstraction, right? Lambda abstraction says, if you can give me a real world function from models of values of type A to models of values of type B, then I can give you a model of functions from A to B. Okay, so you can think of lambda abstraction in application as inverse in this sense. Okay, so I've said some of this already. Compare higher order abstract syntax with applicative. We have the sequencing operator from applicative. I guess the composition operator, it's not sequencing in general, but we don't have pure. Right? To have pure would mean that we could take everything in Haskell and lift it up. And I could take any A from Haskell and interpret all of Haskell inside this language, but I don't necessarily want to do that. Okay, that's too many terms. I only want the terms that I'm going to provide to the user. Maybe I do, maybe I don't. In the case I'm going to go through, I don't. I won't be able to implement this class if I choose to implement pure. And this lambda abstraction looks like an inverse for applicative composition.
Can you pronounce that $$ operator there?
Oh, well, I mean, dollar's taken, right? So I just call it like apply, but it turns out to be neat when you write these terms out to be able to write this. Okay, so lam, you can think of, this is regular Haskell functions on the left, right? And then this is kind of our weird functions on the right, like our model functions. But we're embedding the entire Haskell function space inside our function space, okay? So our values, like we don't have a term for lambda calculus names here, right? Because I'm just going to use Haskell's names. The name for FA is going to be the name I'm going to use. Okay. What interpretations do we have for this? Well, if you just erase all the F's, okay, then those look like functions that we already have in Haskell. This is just function application, and this is lambda abstraction in Haskell. So I can interpret this in like the F that does nothing, right? FA equals A. So that's one interpretation. I can interpret HOAS as regular Haskell values. But we can give other interpretations, right? So one interpretation is to pretty print. So here's an implementation. Okay. So here's my class. Here's some terms that are polymorphic in the particular representation that I chose. So for any F, I'm going to construct a model of a function from A to B to A. So the typical function, if there was no F here in Haskell, would be the constant function. Okay. So I'll call it K with a const with a K, so I don't step on the names. But it's a lambda abstraction that takes A to a lambda abstraction that takes, I wrote it like this, something to A. Okay. You can say B if you like, but we don't use it. So we have a model of the constant function. We have a model of application. So anything that you can build up in Haskell, any function in Haskell that you can only write as application and lambda abstraction, you can certainly write here, right? I can just translate everything term-wise, just structurally, bottom up. But you can't write everything in Haskell, right? I don't have tuples in my language, so I can't write the tupling operator. I'd have to build that in. So here's the application combinator, right? It's a function that takes, it's a model of a function from A's to functions to B's. And I just do the thing you'd expect, right? But then, so I can interpret these in Haskell, but I can also interpret them in different ways. I can choose different interpretations. So here's a pretty printing interpretation. So pretty printing takes, because I don't have any names in my representation, I need to use an integer to just generate fresh names, right? So this is just a technicality, but essentially this boils down to I'm going to interpret these things as strings and just print them. So let's do that. GHCI, what did I call it? Pretty print. constant function maybe. Oh, I give it an integer. Okay, so 0. Okay, so I'm interpreting my language by just pretty printing it, right? This looks a little bit like code gen, right? If I tweak this a little bit, I could get it to generate JavaScript, or I could get it to generate C or something, right? So we've completely skipped parsing. We've completely skipped well, lexing and those lexing and parsing and those initial things that I talked about, right? Do we need to choose a sensible type system? Well, no, because we're using Haskell's type system, right? This won't type check if, well, let's write something that doesn't type check. Can I apply A to itself? Is that a valid lambda calculus term? No, because it has an infinite type, right? The function argument type ends up unifying with itself. Ends up unifying with the function type. So you end up with this infinite function type, so it's not a valid term. So we piggybacking off the Haskell type system, right? So the Haskell type system tells us, no, that's invalid. What else is an invalid, poorly typed term? Oops. So this one does type. Yeah, so here's one, right? So if I try to apply, that one will work too. I'm sorry, it actually, because it's kind of so, you have to kind of work pretty hard to make it not type check. The types are going to be horrible, but yeah, you have to work quite hard. But yeah, we're doing code generation here, right? So we've completely, essentially skipped code gen. We've written a really tiny programming language in, what, 20 lines? It doesn't do much, right? But then you can build things on top of this. So yeah, time permitting, I was going to actually try and turn this into like a JavaScript code generator. So we've got time, right? I'll go through that. All right. Okay, so there's a little bit of kind of noise with this integer, and to avoid parenthesizing things unnecessarily, I also track. We have this notion that we had when we did the document thing. We can always extend things and we can add more functionality as long as we can still interpret the rules right. So I choose to add to my model whether or not the printout is, I called it atomic, right? So you can think of that as like, is it a string with no spaces? If it's a string with spaces, then when I embed it inside a function application, then I'm going to have to parenthesize it. So this is just a cheap way of telling me, do I need to add parens whenever I apply a function to this thing? Okay. So in order to be a member of this host type class, then we just need to, then this pretty print type just needs to be able to interpret function application and lambda abstraction. Right? How do I apply one term to another? Well, I take my fresh name generator, that was this integer. By the way, these, if it wasn't obvious, these are the integers that are getting generated, right? This 0 and 1, 1, 1, 0. That's why I need the integer there, because I don't have a name supply. So I take my name supply I, okay. So then I apply f, which was my first function. So I give it the I, my name supply, and I say generate me a string, okay. I may need to parenthesize it. So parenthesization just happens when the term is, when it's not atomic, right? So I use this at, I pass it to this parens function, and if it was not atomic, it's a false, then I add parens, and that's all that's happening there. Okay. So I take my first term, I parenthesize it possibly, I render it with this application in the middle, and I possibly parenthesize the application to my second term. Is it atomic? No, right? Because I definitely have spaces in there. If I want to insert this into a function application, I'm definitely going to have to parenthesize it. Lambda abstraction. So lambda abstraction takes a regular Haskell function. So this one's a little more complicated, and you have to give back a term. Okay, so my terms are pretty printing values. So I take my name supply, and the first thing I print is the lambda piece. Okay, and I need a name for my variable, so I just pick the thing that comes out of my name supply, and I'm going to increment this when I pass it on to things inside this term. So I say lambda a, and I name it a0, a1, etc. I just show the index that comes out of my name supply. Print the arrow, and then I pretty print whatever So this was a function that took models of values to models of values. Okay, and I need to give back a model of a function. So I have to come up with some model of a value. Well, I can pass to f the model which just ignores the name supply and just prints out a with the name that I got out of the name supply out here. Right? So I've claused over I. Is it atomic? Yes, it's just a name. And then it's cut off, but it's I plus 1, so I bump the name supply when I go inside to print the body. And the result is not atomic, right? Because there's definitely spaces in here. Okay, so there's a little bit of noise because of the int stuff and the atomic stuff, but I mean, it's not too bad, and the result's quite nice, right? But then you can turn this into a code generator for, like, let's say JavaScript, right? So let's say how would we do that? Okay, so application in JavaScript doesn't look like that. Right? It looks like this. But we don't need to parenthesize here because we're inside parentheses. Okay. I do need to parenthesize this because there might be, let's say, a function as my first argument. Okay, and lambda abstraction doesn't look like lam. It looks like this. So it's a function from AI, and we have a body. And we return whatever the pretty printer gives us. Got to get the parens right here. There. Is that right? Yep. Is that right? Seems about right. Okay. So that's a code generator for JavaScript, right? And like, it wasn't very hard. But that's valid JavaScript, right? And it's parenthesized nicely, and it type checked it and everything, right? So we've built a prototype language, and it's 20 lines long. So like Haskell's type system affords us a lot of expressiveness, right? It's really nice. So let's add some features, right? You said, like, in practice you would never write programs in this language, right? You might, but it wouldn't be particularly pleasant. So let's add some booleans. Okay, so I need a true value. True. Oh, well, no, I can use true, right? Because it's capital true in Haskell. So I need a term true. That's a model of a boolean. I need a false. That's a model of a boolean. What else can we do with booleans? So we can AND them together, but I guess the more interesting thing is we can do an if then else, right? So if then else is going to be, let's make sure I get this right. You got to, so it can be it can be a model of a function, or it can be a function between models, right? So I just got to make sure I do the right one. So that's the type of if then else, right? So I want a model of a function from booleans to two values, the true value and the false value, and depending on whether the argument was true or false, I'm going to give you back left or right. Okay. So this will compile, but it'll complain that I didn't implement those three things. That's fine. Let's go and implement them. Oh, come on, I'll do it here. Can you tell I'm really, really bad at Vim? All right, true. The implementation of true is going to be, I'm going to implement it in terms of pretty print. So, so what's the string value? Well, I don't need a name supply, so it's a constant function. And in JavaScript, it looks like true. Is it atomic? Yep. False. What's that? Well, that's constantly false. Quick type check.
It is true.
Oh, thank you. Boolean blindness problem, I guess. I don't know. All right, if then else. Oh, that should be ITE. Oh, let's give it a proper name. If then else. Actually, this is going to be kind of noisy, isn't it? Because I'm going to end up writing 3 functions in JavaScript, which is going to be pretty horrible.
Can you just do a turnaround murder?
Yeah, but I'm still, my interpretation of the function space is function A, function B in JavaScript, right? Which is going to be irritating to write out. So maybe we'll do it this way instead. Okay. Okay, so we have a term for the conditional. We have a term for the true thing. Actually, I don't need any of these. I just need the terms. And we have a term for the false thing. Okay, so I take my fresh name supply. Okay, so I have to pretty print the conditional with my name supply, and then use the ternary like we said. Pretty print the true thing with the name supply, use the other part of the ternary. Pretty print. What's that say? Did I misspell? Okay, it'll tell me, I guess. Pretty print the false thing with the name supply. And is that atomic? No. Okay, hopefully this type checks. Nope. Pretty print with int string in 26.146.
Write it pretty, yeah.
What was that, sorry?
T-print.
No, that's okay. That's the name of my constructor. That's fine. Oh, right. No, pretty print's right. There's an integer argument missing somewhere.
Is pretty print trying to consume const?
Oh, it is. You're right. Thank you. Yeah, did far too much typing. Thanks. Good. All right. So now we have a bigger language, right? So I can write the not function, for example. Here's the not function in JavaScript. Pretty print lambda b goes to if then else. If b, then well, no, I have to apply, right? It's the way I. Oh no, I didn't do it that way. This is good. So if b, then false, else true. Need a name supply. Okay, cool. So there's we've extended our language with booleans, right? So you can add all sorts of stuff. You can add other primitives for booleans like and or not. You could add integer arithmetic. You could add things like less than, greater than. But this is a nice way to kind of bootstrap a language and just build a prototype quickly. What else was I going to say about this? So one project I have that's in the works but not really quite working yet. It's an application of this idea. So I work on the PureScript compiler, and one library that we ported to PureScript from Haskell was Parsec, but it's kind of slow, right? So the implementation of Parsec in JavaScript is slow just because of the way it's implemented, right? There's a lot of combinators and lots of function applications and abstractions. But a lot of the parsers that I'm interested in writing could be statically generated, right? They're really basic, right? You could just write basically like applicative is enough, right? I don't need a whole monad. But so if I can pick the right abstraction for my DSL for parsing, so that I can do enough static analysis, maybe I could just even choose maybe I could choose an interpretation that actually just generated JavaScript, right? Maybe I could use this higher order abstract syntax to just generate. Instead of actually turning it into PureScript functions, I turn it into JavaScript and use use eval in JavaScript to actually turn it into a function, right? And that's safe because I type checked it in PureScript because the type system told me it was safe, and it was safe at compile time, so it's fine to eval it. So that's like a practical application of this that I'm currently working on, but we'll see. Hopefully it'll work out. And just quick demonstration that like this isn't just kind of theoretical. So here's like a bit. Here's like a work project I'm working on, right? This is like an extension of the routes example, the route table, right? So I was using the applicative, so a little bit more syntactic sugar here to make things a little more easy to read. But this is a REST API, right? And so I'm saying I'm using applicative to build up routes here. So my route is session login as a post, and I have a JSON request body, and I have a JSON response body, and things like this. Right? I'm using applicative to build these things up, and the way I built this thing was it is here. PureScript REST. The way I built it was exactly how I did all of these examples. Right? Here's my endpoint class. I just choose the primitives that I need in my language. I have a way of asserting what the HTTP method was. I have a way of matching literals. That was like the string thing in our routing table thing. I have a way of matching things inside the routes. I can match query parameters. I can match headers in the request. I can get the JSON request and get the JSON response. And then there's other like niceties, like I can add comments for documentation, right? But the nice thing is I can choose to interpret this endpoint as a node HTTP web server, but I can also choose a completely different interpretation, and I'm free to choose that interpretation because I'm using this finally tagless style. One other interpretation I have is...
Can you remind me what finally tagless means?
Yeah, finally tagless was this idea that I'm choosing my type class and then picking multiple interpretations, like we did with applicative and we did with monoid and monad. So I start with applicative, and my endpoint class is built on top of it by adding, so my notion of composition was given by applicative. My primitives are given here. All right. Another interpretation is this is a bit dense. Let's do. Oh well, I need to load it up. This is the website I'm building with it, right? So it gets turned into a website, but it also gets turned into static documentation. So all the route parameters get written out as comments. All the headers get written out as documentation. Here's the example request. Here's the example response. Here's the API tester, right? It all gets hooked up. So you have this idea of like multiple interpretations. And that's kind of the crux of this finally tagless style. So yeah, those are like my two favorite EDSL approaches. So yeah.
I still don't understand what you mean by multiple interpretations.
So, so in my, I guess so let's go through the examples, right? In the monoid case, which was the document one, I said the default interpretation is going to be an actual document, right, like a list of strings. But I might choose to interpret it just to see if it fits on the screen width, just as an integer, right? That just takes the width and just forgets about the structure. So that's a separate interpretation. In the applicative case, my default interpretation was a route parser, but I could have chosen, and I have an implementation, but I didn't show it. So the one I went through was match route. Okay, so match route was this thing that took the list of strings and maybe gave me an A in an unmatched tail. I can give a completely separate interpretation, which is printing the routes. So you can think of this as a really cut down version of the application I was just showing, right? Matching the routes is running the web service, and printing the routes is documenting them. So instead of generating a value of type A, I'm just going to generate, again, I need a name supply, right? So that's why the int's there, but essentially I'm just generating a list of strings just to print out the routes.
So I thought you were going to say there's one data type that I can interpret two different ways, but it seems like you're saying there's these two different data types.
There's one class that I can give multiple instances for, and the instances are like the interpretations. Yeah. So in the match route case, do I have it? Be up here somewhere. Yeah, I needed that. So I said I could match a route. Right, and that was when I had foo bar baz bam, and I was getting out bar bam. But I can also render a route. So let's render this. Right, and I'm just making up names for my matches here. So you can think of this as like a really cut down version of that documentation versus actual implementation example that I was going through. the monad case, we were interpreting in I/O versus interpreting in the fake file system. In the Hoas case, we were interpreting in Haskell versus interpreting as, let's say, JavaScript code gen. So yeah, finally, Tagless is all about this like one spec, multiple interpretations idea. And it's really powerful, right? It gets you a really long way. And then, like I say, Hoas is like one of my other favorite techniques. So there's papers about both. Wikipedia has a nice article about higher order abstract syntax. It's worth looking at. And the paper by Oleg Kiselyov. Finally, Tagless. That's it. Finally, Tagless partially evaluated. Does a much better job of explaining it than I did. But yeah, this is really worth reading. It's a really good paper. So that's it. I can answer questions if you want, but I'm done. All right, thanks.
So it felt like we were at the end there mapping everything in some sort of container to say expression. So then the parser is just the thing that's going to, or not the parser. Yeah, I guess Lexer parser is going to be the thing that, where you can write a simpler language and turn it into that. Right?
Yeah. So I mean, depending on your application, this may be good for prototyping only, or it might be the way you implement your language. Right? I mean, the trade-off is you can write a language in 20 lines versus, well, I mean, practically, like maybe less than 100, but versus you have to force the Haskell runtime on your users because you're embedded in Haskell. But yeah, so I completely skipped parsing and lexing because I just get them for free because I'm embedded in Haskell.
But the trade-off is that we're writing the containers for each expression.
Yeah, so, well, with the host one, yeah. So with the file system one, did I close? I guess I closed it, that's fine. With the file system one though, it was it was in Haskell, but I had the full Haskell language at my disposal, right? And the reason for that difference was because in Hoas I chose to omit pure from my type class, right? I can't lift up Haskell into my language, but with a monad I have return, applicative I have pure, so I can lift up all of Haskell and I can use the whole Haskell standard library. I don't want to, if you think about the Hoas example, yeah, if I put pure in here, right? And I try and pretty print it, I lose all my analysis, right? I can't pretty print an arbitrary A, right? If I think of a function, I can't. If I have A to B, I can't peer inside the implementation of machine code and then pretty print it into JavaScript. So omitting pure buys us a lot of static analysis. Yeah.
Is this finally tagless style of building DSL? Could you see it as an alternative to building a DSL using a free monad? Are those two concepts No,
they're definitely related. So finally tagless is a pun on final, as in technical term, I guess, in terms of it's a technical term, like it's a final encoding of a data type, right? There's also an initial encoding, right? If you replaced class with data here and scrubbed a few bits out, this would be constructed for a GADT, and that's the initial encoding. Okay. And it's also related, if I took that GADT and made the free monad out of that GADT, the functor that gave, this might be wrong, but then you can express the same programs in that free monad as you can in any monad file system, I think.
You're familiar with both approaches, I presume. Do you dig this more than doing the same thing with the free monad? I've never seen this stuff.
I really like this. I just think this is really neat, and it's GADTs are another option. You could write this in terms of GADTs, right? So you just define your term language where these type equalities here are expressed in terms of GADT instead. This is one reason I really like this is that PureScript has type classes but doesn't have GADTs, right? So I can write all of these things in PureScript, but I can't write them in GADT style. So you can actually think of this as a way of encoding GADTs in a language that doesn't have them, which is how I use them a lot of the time.
Personally, the mental overhead of understanding this relative to the moral equivalent with free monad seems lower to me.
Right. I mean, I think also, like, depending on your attitude towards like type class laws and things, you might want to structure this in such a way that, you know, you give your specification laws and stuff, and then you start proving things about it in terms of the base abstractions and things.
Cool.
Of course, you could do that with GADTs as well, but I guess you typically tend to do that more with type classes, although I'm not sure why.
Do you have reference to learn more about the HOAS idea?
Yeah, so it's on Wikipedia. I think it's not a terrible article.
Roy Fielding wrote a paper about it?
Yeah, the CMU paper is probably the one to look at.
Associations.
Yeah, Frank Fenning and here you go. I would probably start with this one, which I admit I have not read. But this looks fairly foundational. The place where I actually started learning about this. So an ex-colleague of mine, where is it? Embedding of linear lambda calculus. Here it is. Yep. So an ex-colleague of mine wrote this paper, and it went to ICFP, Haskell Symposium this year. I don't know if you're familiar with linear lambda calculus, but linear lambda calculus is a... so we said what lambda calculus was, and we had lambda abstraction and application, right? So this looks pretty much exactly what we wrote earlier. Linear lambda calculus is an example of a substructural lambda calculus, substructural logic, where you restrict the usage of the names inside the terms. So in linear lambda calculus, you can so every name can only be used exactly once, right? So lambda a goes to a as a fine linear lambda term, and so is lambda f a goes to f applied to a. That's fine because f got used once and a got used once. But lambda f a goes to f of a applied to a second time is not good because I used a twice. So linear lambda calculus is good for a few things, but it's good for talking about resource management. So if you know that everything is only used once, then you can do neat things like you can garbage collect. You can just free its memory as soon as it's used the first time. People talk about resource logics, linear lambda calculus, right? So you can think of passing dollars around, right? So a function from $1 to a can of Coke, right, is fine, but I can't use the dollar twice. So I can't use $1 and then buy a second can of Coke with it because I can apply the function twice. So so linear lambda calculus is good at modeling resource usage generally, but it's really hard to embed it in Haskell, right? You can't write linear lambda terms in Haskell because Haskell by its nature lets you use names multiple times. So this paper talks about how to embed it by using a HOAS style, a finally tagless, there it is, tagless final encodings, HOAS. So I learned about these two ideas from this paper. And then what's really neat about this is that if you ever read type theory papers, right, you get things like this, type system explanations. The Haskell code looks like a verbatim, it looks exactly like this, right? If you just translated this into Haskell code, it's line for line, it's very neat. So yeah, this is a neat paper too, very much recommended.
Earlier you said this can be, you said this, Peter, basically this can be used to write a language really quickly.
Mm-hmm.
When you say this, what is this referring to?
Just these techniques in general. So
I wrote down two buzzwords.
Yeah.
It was
finally
tagless and
higher order
abstract syntax. Is that
right?
all of them?
So this one, this paper develops. So linear lambda calculus is a language. It develops a whole linear lambda calculus in a very short amount of Haskell. They're really good techniques for prototyping languages. But if you want to, you can turn them into sort of real languages embedded in Haskell. Just needs a little bit more work. But yeah, so I mean, the talk was just trying to sort of take all these techniques, so like the MTL style with monad and generalizing that to applicative and monoid and these various notions of composition. And then HOAS is a little bit different, but it works nicely with final tagless style. So I just wanted to kind of show a few examples. Yeah.
Sorry, to piggyback on Aaron's earlier question, or his comment, it's kind of sinking in. The GADT style of representing things
Yep.
is representing things as actual values and structure,
Right.
whereas the other style is either
Functions, essentially.
Yeah. Function application,
Mm-hmm.
whether or not it's fully applied or partially applied.
Right.
But it's still representing the same data. It's still representing
Right.
the same flow. You just, one of them is more like you pass a value, you get a result, versus like you have to then somehow evaluate this thing.
Right.
Is this thing more the initial representation and this is closer to the final representation, or is final representation not even relating to here because you can't actually extract a structure again?
So,
Or is this a completely nonsense question?
no, I think I need to maybe pick it apart a bit, but yeah. So with GADTs, you know, the data's right there, right? Like you can pattern match on it, and that you're dealing with values. Like you say, you're dealing with functions, essentially type class dictionary functions, right? When you talk about the final tag, the final version, right? In order to do your interpretations, you have to write a type class instance. So you can think of writing the type class instance as analogous to pattern matching out the GADT. When you pattern match on the GADT, you get type equalities asserted. You know, I was doing my type checking in the type class by because my type class instances had to satisfy the type equalities given by the instance members. The same type equalities would be asserted by GADTs, but you don't have to write an instance to do it. So it's a little more lightweight, I guess, in that sense. I don't know if that answered your question, but that's
No, actually, yeah.
Okay.
It helped. Thanks.
All right. Cool. Yeah. Sure. Sure. All right. So.
Yeah, I was a little bit down.
All right. So here's a GADT. HS module name word. All right. So GADTs are not Haskell 98. They're not GHC standard Haskell, I guess. So you have to turn them on with a pragma like this. Okay. GHCI, GADT.
Is there an elevator pitch for what they give you or what they solve?
Yeah. I'll try and go through it. I'll try and motivate them. Okay, let's get this right. Okay. Well, I'll just, yeah, so here's a quick introduction. Here's an algebraic data type. Okay. Here is another one. Hold that in here. Give me the type of foo. Okay, foo is a function from strings to foo. Oh, I shouldn't have named them the same thing.
Can you hit L every so often, just so that your body's not blocking?
Oh, sorry. Better?
Yeah.
All right. So that's the type of foo. Okay. What's the type of? Sorry, that's the type of bar. And what's the type of baz? Okay. So instead of writing those out in ADT notation, let's just write them out as we saw them in GHCI. So I just list the constructors. Okay. So baz doesn't take anything, it's just a foo. Okay, same thing, okay. Right, what if I do the same thing again, but I do it with a list, let's say. So let's make our own list. List of A is either an empty list or it's non-empty. Non-empty list consists of an A and another list. Okay, single linked list. Good. Let's make it into a GADT. Where, so empty has type list A for any A. Non-empty takes an A to a list of A to a list of A. Okay. All right. But notice something about these types. A on the right here, list of A is always the same thing. Okay.
Yeah.
How about let's say we want to track the length of the list. Okay, so let's come up with some extra types. We want a type to track 0 length and a type to track 1 plus some length. Okay. So empty has length 0. Okay. And if I take something of length n, then non-empty has length 1 plus n. List is applied to too many arguments. Oh yeah, sorry. Need an n here. Okay, cool.
Can I look at that for a few more
Yeah,
seconds?
sorry. Yeah, go ahead. So you can't write this with regular algebraic data types, right? Because we said the A on the right has to be the same A. It has to just be a generic A. But here we were asserting that it's not just any n, it's 0, and here it's not this n, it's 1 plus n. So you have these type of qualities, and they're the same type of qualities that you would have got in the finally tagless style from the instance members of the type class that you picked when you type checked against the instance type. All right, so why is that useful? Quick motivating example. I can say things like non-empty 1 empty has type list of 1 plus 0 of int. Yeah, okay, type checks, good. Right, so I can assert length of lists. Now I can write things like, what's an example? Right, so the head of a list is in Haskell has this type, right? But when you apply it to an empty thing, it's unsafe, right? So let's write a safe function. List. If the length of the list is at least 1, i.e. 1 plus n for some m, then I know it's safe. And the type checker can even verify it for me. Right, so if I were to try and write this, that would be a type error, because 1 plus n is not 0 for any n. Okay, but this is fine. So the answer to the question, what's the motivation, why is it useful, is that just like the type system allows us to prove things about our programs, we've just enlarged the space of things we can say about our program. Yeah. Yeah. So you could write this in a dependently typed language, where instead of making 0 and 1 plus in the type language, you just use the regular value level integer addition. Literally 1 plus, right? If you're in Idris, you might write this as that, right? So yeah, that's GADTs. And there's a relationship to the finally tagless stuff, because I was saying if you replace data with class, this is starting to look a lot like, well, not in this particular case, but I don't know. We had like monad, horse is the best example, right? Horse f where, and then we had application was what, f of a to b, f a to fb. You could, and you had lambda abstraction as well. You can literally just turn this into a GADT like this. Right? There's a type constructor missing there somewhere, but you hopefully get the point. So yeah, that's GADTs. So, any other questions?
So you get the undecidability problem at the type level?
No, I don't think so. The theory is just the theory of first order unification, right? It's the same thing as yeah. So it depends what you want to say, I guess. You could use type classes to say a lot more, right? So you could say things like concatenating a list of length n and a list of length m gives me a list of length n plus m. So then you need a theory at your type level that can express addition and those kinds of things. and quality is about addition. So hopefully whatever theory you choose to write in your type classes, you write in this way is decidable, right? Because that means type checking is going to terminate. But I think just the stuff I showed, if you just stick to sort of like vanilla unification, then it's definitely decidable. Yeah, that's it. So, you good?
Thank you.
So A is string-like if you have a function called from strings to A. Okay. So in my case, I want my document type A to have a function from strings into the document type. So this is exactly what we want, right? We want to be able to lift strings into our document type. So something document-like is something that is monoidal. It allows you to lift strings, and then I also added these two things. Okay. So I want to be able to indent documents. I want to take a document A and take an indent amount, which is an integer, which is, let's say, the number of character columns, and get a new document. And I already have this vertical notion of composition, but it'd be nice if I could compose things beside each other as well. Right? So I can take two documents and just stick them beside with no overlaps. So I'm going to have to pad the left document sufficiently so that there's no character overlaps. Okay, so here's a class for things that look like documents. Given that class, actually I'll just leave that on the top. Given that class, we can write things which use a document implementation, but they don't care which one, right? So this is polymorphic. This columns value here is a document that's polymorphic in the document interpretation, right? So columns consists of column 1 beside a space beside column 2, and column 1 is Haskell vertically composed with C versus composed with Prolog, and the same thing for these three things, right? So let's run that. So that's in monoid.hs. I think I called it render. Okay, so first of all, what's the type of render? So render takes a plain text. So plain text is my implementation of a document, okay? So render columns. Oh, so I want to print it. Okay, so here's that document printed in some standard interpretation of that type class, okay? So hopefully you see how this corresponds to what I wrote. So you have two columns, I place them beside each other, and each one consists of three things vertically composed, and there's a space in the middle. They're both beside a space, okay? So notice that, well, it's not really important for this, but the vertical composition is non-overlapping, okay? That's built into the implementation. Okay, so we said our candidate was going to be a list of strings, right? So we can write an instance of document for list of strings. We just do the obvious things, okay? So is string a string? Sure it is. The identity function tells you it's a string, okay? Is string a monoid? Yes. Sorry, is list of string a monoid? Yes. We just concatenate the strings one after the other, okay? And if you interpret the list of strings as the lines on your terminal, then that's the vertical composition that we wanted, right? Can we indent a list of strings? Sure, the map function. So if I replicate the number of spaces I want and then map that over my list of strings, just insert a number of characters on the front, space characters, that'll do the job. Can I implement besides? So if I have two lists of strings that represent rows on the terminal and I need to pad them, well, sure. So I can use zip width or a variant of zip width, right? Zip the two implementations of the text, but you run into a problem. How do you get this nice padding behavior here? So there's a trade-off here, and we'll see the trade-off. Whether or not you get more or less static analysis compared to the expressiveness of the language, depending on the abstraction you pick. Okay, so that's the introduction. And this is kind of exercise 1, if you like. So the first type class of composition I'm going to talk about is the monoid type class. So is anybody not familiar with monoid, first of all? I mean, yeah. Okay, right, so. All right, so we'll just go to GHCI and ask GHCI what a monoid is. Is this visible to everyone? Yes. Okay, cool. So here's the monoid definition from GHCI. It's defined in the prelude. So a monoid is defined for a type A. and it's a very basic notion of composition. Okay, so you have an empty element that has type A, and given any two elements of type A, you can create a third one. Okay, so ignore mconcat because mconcat can be defined in terms of these two fairly easily. But hopefully, it's pretty obvious that like this is very generic, right? And lots of things are monoids. So strings, for example, if you want an empty string, well, the empty string is the empty string. And if you want to append two strings, well, you just take the two strings and stick them together. Okay. If you have a list of A for any A, that's also a monoid because an empty list is the empty element. And to append two lists is just to concatenate them endwise, right? So this is generic, but it's given meaning by its type class laws. Okay. So you want to sort of study this in generality, and the way you do it is to say, I want my monoid to satisfy two laws. So if I m append the empty thing onto something, then it shouldn't change what you started with. And if you take three things, then it doesn't matter what order you append them in, right? So if I take three strings, it doesn't matter if I do the first two and append them and then append the third one, or if I append the second two and then append the third one, append the first one on the front, right? You get the same thing either way. And the empty string, when you append it onto something, doesn't change it. So then we say string is a valid monoid, right? And we can check lots of other things are valid monoids too. So monoid is kind of like one of the simplest Haskell notions of composition, okay? So suppose our exercise is we want to lay out textual documents on the screen, and we want to define a domain-specific language for laying out those documents on the screen, okay? So we go back to the properties. We want it to ideally be these things, okay? We want to have familiar syntax. We want to be composable. We want to be able to take two documents and compose them in various ways, in nice ways. We want it to be typed, but in this case, and this really goes with it being a monoid and not something else, there isn't really a good notion of typing. If you think about like what type does this textual document have, it doesn't really have a good answer. So we're going to ignore B types for now. And static analysis, we'll get to that as well. So static analysis in this case might be, here's a document. Tell me if it contains any links, or here's a document. Tell me if everything fits into this page width, for example. Can I display it on the screen? So those are things that are statically determined. You want to know them at compile time, or rather, you want to know them, let's say, before execution, which in the case of a document means before rendering, right? So how do you know that C has to be indented by what, 6 characters? List of string isn't enough, so we need to actually add more information to our representation. And here's the representation. So we just add on, here's the list of strings that we wanted, and we just add on the document width as an integer property, okay? So in this case, the free implementation was not quite enough to do exactly what we wanted. We could have implemented something with the free implementation, but it would have ended up so that you didn't get the nice sort of padding property when you did horizontal composition. So the point is we can, given this document type class, so we pick, so this is going to be like the motivation for the rest, right? We start with a class that uses standard notions of composition. So we started with monoid because that's the composition we wanted. We built up a class that determined the sort of operations we wanted on our candidates for our carrier type for our documents, okay? But we can pick multiple implementations, right? So we could have picked the free implementation, which was list of string, but we picked this one because it allowed us to render slightly nicer documents, okay? But you can also ignore structure, right? So we added structure here. That was adding an integer width. But we could take structure away, right? Maybe I only care about the width, and I don't even care about the lines. Maybe I just want to sort of simulate rendering something, right? Just to answer the question, does this fit inside a given width? And that answers the static analysis question, right? So we can pick instances for our type class that do more or less than the original task. We're just trying to sort of abstract over the operations that we're interested in, right? And that's what this type class approach does. Okay, any questions? Because I'm gonna do a few more examples. It's gonna ramp up a bit. Yep.
What's the double caret operator on that?
Oh, right, this one? That is just a synonym for, or I guess it doesn't tell you, but it's a synonym for mappend in the monoid type class. So if that wasn't clear, sorry. So here is where we're doing our sort of standard monoidal concatenation, and we said that would correspond to vertical composition. Any other questions? Okay, so the gist of the talk is going to be I'm going to set a bunch of DSL related problems and kind of solve them all in this way. And you'll sort of see the trade-offs given the properties that we wanted. You'll have various trade-offs for those properties. Okay, any questions before I carry on?
Actually, I have one question. So we're tracking the width, but it seems like we could calculate the document width from, like, by taking max, width of the other ones.
Yeah, I guess you could do that. That's a good point. Yeah, so you should do that, I suppose.
Would that be less efficient?
Yeah, I mean, I guess you can consider it an optimization in that case, right? Atom. Oh, well. So here's my implementation. So it just turns out well, beside was sufficiently complicated, right? I had to do a variant of zip width and all these kinds of things, yeah. So you'd have to do a map, right? You have to do a max, and then every time you're interested in finding the width. So I guess you can call it like a small optimization just to save the width. But yeah, I suppose you could just use the free implementation in that case. The properties we want. So going back to that list of desirable characteristics, right? We know we want composition, so we want to compose two documents, and a natural notion of composition of documents is vertical composition, right? So I take text document 1, text document 2, and just stack them on top of each other. And we need an empty document to be a monoid as well. So an empty document is just no text, okay? Empty width, empty height, no text. So we can compose and we have an empty thing, so already we have a monoid, right? So whenever you see monoid in Haskell or other languages, the sort of canonical choice of monoid, like the free monoid technically, is over a type A is a list of A, right? So to explain that, I guess you can say you can always think in terms of lists if you want to have if you want to talk about monoids, you can always think in terms of lists. So that should be our motivating example.
What does free mean?
Free, technically, it's a category theoretical definition, but it means it's intuitively you can think of it as any monoid has an underlying type, right? So there's a mapping from monoids to types. Can I go the other way? Is there a way to take a type and create a monoid in a way such that I satisfy the laws of the class, but I don't add any extra information, I don't make any assumptions that weren't prescribed by the class? Okay, so if you think about given a type A, how do I construct something that has composition and an empty element? Well, a list is a good candidate, but in general it might be something like a tree, right? Because I can compose this and then each branch corresponds to composing two things. But the associativity law that I said, the fact that you can compose any three things in any order means that tree structure kind of gets flattened down and you end up with just a list. The only structure that remains visible is the list. So it's a little technical, but you can think of it as the minimal monoid for a type that doesn't assume any extra laws, if that makes sense. Yeah. I would just say the kind of go-to example, let's say, for a monoid over a type is a list of elements of that type. So we should always have that in the back of our mind. And we know we want to make a string into a document, okay? We want to be able to take any string of text and just turn it into a document that only consists of that string. So why not try the free monoid, the list of A, where A is this thing we want. We want to lift this type up into a monoid. We know we want string, so why not try free monoid for strings or list of string? Looks like a good candidate. So let's extend the type class that we picked for composition, which was monoid, with a couple of extra characteristics that we want our document to have. Okay, so we want our type class to characterize things that are document-like. Okay, so we've said document-like means we have to compose in this monoidal way, right? So we're gonna assume monoid on A. And Haskell in the Prelude has this this class called isString, which essentially corresponds to the assumption that we want to be able to turn strings into documents. Okay, so isString looks like, I might have to import something. Yep. So it's in data.string, and here's from string. Here's isString. I'm going to give a talk that I've been thinking about for a while I think the original meetup.com synopsis of this talk was that I was going to talk about sort of writing a programming language from scratch, sort of like a very minimal programming language. But the more I thought about it, a lot of that. So when you write a programming language in Haskell, you do a few things. You have to use things like parsec to do your parsing and lexing into tokens and then parsing. You have to write a type checker. So you want to you want to parse using parsec, let's say, into some abstract syntax representation. You want to write a type checker that checks that syntax representation to make sure it's sound statically at compile time. You want to do various optimizations. And these are all things that it could be we want to generate code. These are things that could all be talks in their own right? And there's interesting libraries for solving all these problems. So I thought, actually, what I'm going to talk about is I'm going to try and cover two of my favorite techniques for writing embedded DSLs in Haskell. So the title of the talk is How to Not Write a Programming Language, parenthesized, not such that I'm going to tell you how to write a bad programming language, but how to avoid writing a programming language in Haskell. So you might, for one reason or another, decide that you want to write a programming language, or that you need a pretty expressive DSL, so you consider writing a programming language. But then the alternative is to sort of leverage the techniques and the power of Haskell to write the language inside Haskell, and that's the embedded approach. Okay, so we get to cut out a lot of these different steps here. So if we're living inside Haskell, if our language is embedded inside Haskell, we don't have to lex anything, we don't have to parse anything, right? Because our syntax is Haskell syntax. We don't have to choose a sensible type system because we're already embedded in a great type system, the Haskell type system. Okay? Type checking comes for free because we just make GXE do it for us. Optimization, we may want to still do some optimization, and we still need to do code generation. But we've reduced the problem space significantly, right? We only have to concern ourselves with transformations and functions out of our syntax representation. Oh, so I should say, stop me whenever. Should be hopefully pretty informal. I have some code samples. We'll just walk through them, and if anything's not clear, just let me know. I tried to sort of make it as simple as possible, assuming that you know at least type classes and let's say higher kind of types in Haskell. So things like monad, for example. Okay, so we have some problem domain, and we've decided to write an embedded domain-specific language. We picked some terms, aka the syntax representation, for our language. And what properties do we want those to have? Well, we want to have familiar syntax. Well, that's good because we're embedded in Haskell, so if anyone's familiar with Haskell or ML-looking things, they're going to be able to use this language already. We want it to be composable. We want the terms of our language to be composable, so this is going to actually motivate our various examples, and each jumping off point will be one notion of composability, and then we'll go from there. We want our term representation ideally to be typed. They may or may not be typed, but this may be this may be beneficial, right? So we'll talk about that. And we want terms to support static analysis.